air, and water. Powerful friends at rest. Fearful demons when aroused. Primitive man recognized them as vital to life and worshiped them as gods. Modern man also knows them as vital to life, but accepts them as commonplace. Yet to men like Ed Lustenauer and Ted Rich, there's much to learn about the commonplace. These men and engineers at General Electric are among thousands of scientists and engineers across the nation who are seeking new knowledge from common things. Ed Lustenauer, why are you interested in studying water?
We're hoping to develop a method for converting seawater or brackish water into fresh water. You're probably wondering why we're doing this. We can probably see this best from a curve of our water usage projections for the United States. This shows the billions of gallons of water that we use each day plotted against years. And we see that our water usage is increasing. It's in pace with the greater industrial activity, the increased population growth, and the increased water consumption per person as our standard of living increases. By 1960, we used about 300 billion gallons of fresh water each day. By 1980, we expect to use about 500 billion gallons of water each day. And this is about equal to the amount that we can easily recover from rainfall. Now, neither our population nor our water supplies are equally distributed across the United States. So as a result, we have water shortages in many areas.
I get the impression from what you've just said that you're not only concerned with seawater, Ed.
No, we are concerned with cleaning up other types of water. Some cities, for example, have water which contains as high as 2,000 parts per million. In these areas, even water softeners are not adequate to clean up the water so that modern appliances such as dishwashers, automatic washers, these cannot be used. Here in our area, we have only 150 parts per million in our water, so that water is not a problem.
Well, now, Ed, just how do you go about purifying water?
Well, there are many ways of doing this, and distillation is probably the oldest and the most common method of doing it. Distillation is basically a process in which we evaporate water by heating it, and then the fresh water vapor that's given off we put to a cold surface and condense it to form fresh water. Let me show you. Here we have a beaker full of seawater. We're boiling this by means of this Bunsen burner. And this water boils at about 214 degrees Fahrenheit. And this is about 2 degrees higher in temperature than the boiling point for water taken from your faucet. Now, the boiling point elevation is due to the fact that we have dissolved salts in the water. The vapor that's coming off, however, is fresh water vapor. And if we hold a cold surface in close proximity to the steam, we find that we get condensate, which is distilled water. The salt content is left behind in the beaker. Now, this distilled water we can use either in our steam iron, can use for our automobile battery, or it can be used for drinking. Now, this is just one method of accomplishing distillation.
Do all these distillation systems work on the same general principle?
No, here at General Electric, we are developing distillation systems of a new concept. Let me show you an example. This is what we call our thin film distillation unit. This will take seawater and convert it into fresh water. Let me show you how this works. It consists of a heat transfer surface, which is about 6 inches in diameter and about 4 foot long. Inside of this surface is a rotating set of wiper blades. We bring seawater in. It flows upward through a hollow wiper shaft to a water distributor. It is then brought out to 4 places at the wall. This view shows where it's distributed just ahead of each set of wiper blades. Now, as this assembly rotates, we spread a very thin film of seawater on the inside of the tube. We then heat the outside of the tube in the area as shown here with steam. When the steam condenses, the heat then passes through the tube. And as we saw before, if we boil seawater, the vapor which is given off is freshwater vapor. We remove this vapor, condense it, and this forms fresh water. The balance of the seawater that remains on the wall is concentrated and flows by gravity and is removed at the base of the unit. Now, this same general concept can be used for large municipal plants. And we can take advantage by combining this with a steam electric power plant and use the waste heat from the steam power plant to reduce the heat load to our water plant. And in this way, we can reduce the cost of fresh water made from seawater.
Water, certainly a household commonplace. And here's a common household nuisance, the lowly cobweb. But this cobweb, formed of dust particles held together by electricity in the air, is telling Ted Rich a great deal about the air we breathe. Ted, why do dust cobwebs interest you?
Well, the dust particles are a visible manifestation of particles in the air, perhaps a very unwelcome one to the average housewife. Actually, this is a result of dirt particles being lined up by an electric field. It may seem like a supremely useless thing to do, but we can make these in the laboratory, and if you want to watch, we'll do it right now. This is some camphor down here, which I'm going to light, and then catch the smoke in this transparent box. This is quite a dirty smoke. We'll give it a little high voltage. Gradually, you're going to see the smoke string together in long, lacy strings and gradually get dirtier and dirtier and heavier and fall out. There we have the start of a very good and dirty cobweb. These cobwebs are made up of fairly large particles. Most of the particles in the air are invisible, and I think I can show you their relationship on this diagram. If we take a bit of air and multiply it 30 million times, the most common size particle in the air, which is about 1/millionth of an inch in diameter, would be the size of a 6-foot man. The smallest particle that you would encounter very often in the air would be about the size of a basketball. And the largest particle would be the size of a 6-story building. Now, the nearest neighbor to this man would be 4 miles away. It's very difficult to believe how small these particles really are. This common-sized particle in the air practically floats. In the course of a whole day, it would only fall about that much.
Where do these particles come from, Ted?
Particles such as this in a city are almost entirely man-made. Anytime there is any combustion of coal or gas or oil or gasoline, there is inevitably some particles produced. For instance, in the rural areas, you'll find only 5,000 particles per cc. In the small suburban towns like Schenectady, perhaps 25,000 cc. But when you get down to a place like LaGuardia Airport, the numbers run up to 100,000 particles per cc. And in the streets of New York or Los Angeles freeways, you can easily encounter 1,000,000 particles per cc.
Excuse me, Ted, but I think I should point out to our audience that when you say cc, you mean cubic centimeter. About the amount of air you could hold in a thimble.
Now, in the country, nature makes some of these particles too, and some of them in rather surprising ways. An ordinary pine forest puts off a gas, and this gas, under the action of sunlight, undergoes a chemical transformation and produces particles. In fact, it's quite well known, this blue haze that one sees over a pine forest. Another fairly good-sized source of particles is the debris that is left when salt spray evaporates over the ocean. Much more rarely, of course, one finds a volcano spewing a lot of particles in the air. And when this happened some years ago, for several years afterward, there were brilliant red sunsets. So, summing up, particles are made in nature by fires, volcanoes, salt spray, and they're primarily made by man in some form of combustion.
How have you been able to get all this information, Ted?
Well, of course, it's been collected over years and years by many different people in many different countries, and it doesn't all come in one fell swoop. Now, in getting information, you usually go through two things. First, you measure what actually exists. Then you try to develop a theory to explain what you saw. And if the theory works, you'll be able to predict what is going to happen, and then you have some mastery of the subject. Now, this recent instrument we have here is one of the things that will be very useful in this whole field. This is called a condensation nuclei meter. Condensation nuclei only means particles on which water will condense, and that covers pretty near any kind of a particle you can find. Now, this particular instrument is now reading the number of nuclei, that is the number of particles in the air. Its full-scale value is 64,000. It's reading nearly a half, or about 30,000 particles per cc. A match, for example, if I light it near the end of this tube, will be sucked in here, and the changes in number will be indicated here. And I don't want to overdo this, so I'll only give it a quick, short burst. You see, off she goes, off scale. Well, that went up into the millions of nuclei per cc, and now it's coming back.
And how do you think this development of yours will benefit us?
There's a lot of ways that it will benefit us. Some of them aren't very romantic. For example, it's obviously an excellent way to check a filter. You can measure the air coming into the filter, measure the air going away, and the difference tells you immediately how good a filter it is. Another thing is insulation, when it is subject to heat and so forth, starts to break down. Well, way before any other method that I know of can detect that breakdown, the nuclei detector will see particles coming off that wire. The most glamorous angle of this is the possibility of its being some use in weather control. Weather control is not as far away as it used to be. The possibility is not around the corner, but it's not hopelessly distant when we can control the amount of rain, perhaps even some of the temperature, and in general make life a lot more convenient and farms and so forth a lot more a safe proposition.
And it must be extremely sensitive, Ted.
If you tried to pick one person out of the 2 billion people in the world, it wouldn't be anywhere near a big enough number to describe this sensitivity. To make it realistic, you would have to be able to pick out one person out of 500,000 worlds of the same number of people as we have. Now, anytime you get that sort of sensitivity, the scientific community is going to find some way to make uses of it other than those that I've outlined.
Well, I can well imagine it must have tremendous possibilities for measurement.
Yes, and this measurement is not a useless thing. The thing I'd like to leave as an idea, or it applies to an awful lot of scientific work and engineering work, is Lord Kelvin's statement. I often say that when you can measure what you are speaking about and express it in numbers, you know something about it. But when you cannot measure it, when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely in your thoughts advanced to the stage of science, whatever the matter may be.
The air we breathe and the water we drink, two of the most familiar things around us in our daily lives. Yet to engineers like Ed Lustenatter and Ted Rich, these commonplace elements hold up the challenge of solving man's problems and meeting his ever-increasing needs.